Alright guys, we are finally wrapping up exponents and logs with section 4.5. We're going to talk about exponential growth and decay. So the first thing we need to talk about is the exponential growth model, and that's given to you right here. And we're going to use that a lot. So let's talk about this in terms of the problem. This is talking about the population of Africa. So we're going to be talking about an initial population and an end population after so much time. K is going to be your either rate of growth or rate of decay. So that's what we're talking about in terms of this problem. All right, so let's plug in some pieces that we know. So this is telling us to write the function that models this data. All right, so we want our population grew to 1,052. Our initial population was 807 million. So we're in terms of millions right now. E to the K, we don't know what K is, but we do know time. So time was from 2000 to 2011. Does 11 years? So we have 11 times whatever K is. So we have to find that K. We have to find that growth rate or decay rate. So we're going to solve this for K. Let's divide both sides by 807. So we got e to the 11k here. Again, I would not reach for my calculator until the very end. Let's take the natural log of both sides. And we can use that power rule, bring that 11k out front. So we have, just copy down this side, 11k times, natural log of e. Times the natural log of e. Now, remember natural log of e to what power is e? That's 1. So we have 11k, we want to get k alone, divide both sides by 11. So this is what you should be typing in your calculator. Natural log of this, close that parenthesis, over 11. And you should get about 0.024. So that's your k value. So we want to write an exponential function for this data. We're going to say A equals 807, that was our initial, e to the 0.024 times time. And that will get us our population at any point in time after 2000. All right, so that's finding our k value, finding our growth rate. In this case, definitely a growth rate, so it's positive. If this was a negative number, it would be a decay rate. Next one says, by which year will Africa's population reach 2,000 million, which is 2 billion. But again, remember, we're in terms of millions, so it's actually nice they put it that way for us. So we want to know, when is this going to reach 2 billion. So we just have to plug it in and solve. Divide both sides by 807. Again, don't reach for that calculator until you are done. We're going to take the natural log of both sides. Alright, so we took the natural log of both sides. We're going to use our power rule. So natural log 2000 equals 0.024t times the natural log of e. Again, e to what power is e? Natural log of e is just 1. So we're going to divide by 0.024. And it's your calculator's time to shine. So I got 38 years. Now, we do want to read the question. It says by which year? It doesn't say how many years. It says by which year. So remember, this is 38 years after 2000. So year 2038 is actually our answer. All right, moving on. Next one is talking about half-life. We're still going to use the same formula. So we still have that same exponential growth and decay formula. But here's the difference. When you're talking about a half-life, in the end, you want half of the beginning. So instead of A, I can say half of A sub 0. I forgot A sub 0 here. Sorry. And so now when you solve this out, when you divide both sides by A of 0, you actually get 1/2. So this is your half-life formula. Okay. Let's plug in our pieces. So we're going to have 28 years is our time, so 1/2 equals e to the 28k. We want to find k again, so we're going to take the natural log of both sides. Bring that exponent down in front, use our power rule. And natural log of e is still 1. Divide both sides by 28. So when you type that into your calculator, you should get negative 0.0248. And we can write our formula. A equals A sub 0 e to the k t. All right, there's my formula. Now we're going to use our formula. So we want it to get down to 10 grams. And we started at 60. We want to know how long it's going to take. So we're going to divide both sides by 6. We get 1/6 over here, or sorry, 60. We get 1/6 over here. We're going to take the natural log of both sides. We're going to use our power rule. I forgot my 8 there. And we remember natural log of e is 1. We divide both sides by negative 0.0248. And when you type this in your calculator, again, make sure you close those parentheses. You should get t is about 72. So it's going to take about 72 years. And it does ask for how long will it take. So it'll take 72 years. All right. Next one, they actually give us a function, and it models the proportion of correct responses after T learning trials. So they teach you how many correct responses. So this says find the correct prior to learning trials. That means you've had no learning trials. So we have 0.8. 1 plus e 0 times this is 0. E to the 0 is 1. So we really have 0.8 divided by 2. So you should get 0.4 correct responses. Find the proportion after 10 learning trials. So we have 0.8, 1 plus e to the negative 0.2 times 10. And when all is said and done, you should get 0.7 correct responses. I'm just putting correct responses CR. Now limiting size. This is basically, it's always going to be that top number. We're going to keep getting closer and closer to that, so 0.8. This next one, I did post a link for a scatter plot where you can just type in the coordinates and it'll do a scatter plot for you. Let me see if it'll let me go to it. So I posted this link on the thing on Google Classroom, typed in my coordinates, and it gave me this plot. So they're asking what kind of model would you use? Well, here I would use a logarithmic model that is logarithmic. Okay, so let me come back here. That is a logarithmic model. So you got to know your graphs for these. So plot these in that scatter plot maker, and it'll do it for you. Next one, they actually gave us the graph. So here, you kind of look at the data and see what's happening. I went from 2.6 to 3, so I went up 0.4. Then I went up 0.7. Then I went up 0.9. Then I went up, it keeps going exponentially up, right? It's going exponentially. You see that exponential growth. So you could use exponential. But also when I look here, I kind of see that linear, right? Kind of see a linear model. So either one of those would work. So two types that would be good choices, exponential or linear. The next one I messed up, so we're actually going to skip problem 6. I don't think I put all the information from the book in it, so my bad. This next one is expressing something, an exponential model in base E. So you can actually take something and you can put it in base E. So we're here, we're going to say y equals a, which is 4, e to the natural log of b, which is 7.8, times x. So that's taking it and putting it back in the form. Now it does say round to 3 decimal places. That means natural log of 7.8. You can actually type that in a calculator. So we're going to have y equals 4e, and then do natural log of 7.8. You get 2.054. So that's 3 decimal places, x. All right, and we put it in base E. So we took something that was not in base E and we put it in base E form. All right, that's it for today. Bye, guys.